So it's a very great pleasure to introduce an old friend, Xiang Tang from Washington University. And he's going to tell us about an index theorem on the tempered dual of a real reductive Lie group.
Thank you very much. So I would like to start my talk by thanking the organizers organizing this wonderful series of seminar talks. It's a really, success. And also giving me the opportunity to speak today. It's an honor and also pleasure to meet friends and colleagues over Zoom. It's kind of a new thing we have having. So today I would like to talk about some of my recent work about the index theorem on the tempered dual of a real reductive Lie group. Okay, so the tempered dual of a real reductive Lie group, this is from the representation theory. So what we found is, well, the tempered dual usually has, is equipped with a natural topology, which I will explain a little bit today in my talk. But this topology usually makes this space into a quite kind of a non-smooth manifold. But what we found is actually there are some nice components, nice pieces we can take out to study their geometry and use them to study some, interesting problems. That's what I hope to share with you today. So in particular, as an application, as I mentioned here, we'll discuss some index problem for proper co-compact G actions. Okay. So here's the plan of my talk. In the first part, I will try to explain to you the motivation and the kind of where we are from, where the example of SL2R to explain you the representation and also index problem. And in the second part, I will try to explain to you the geometry of the tempered dual, the kind of tools we need, and kind of the, as I mentioned, the nice pieces, which we found very interesting to study. And in the last part of my talk, I hope to explain to you some index problem. Okay, so that's the outline of my talk. And here are the, I guess the advantage of talking on Zoom, we can share our collaborators, the photo. Oh, here I see Hessel. So here are the collaborators I have been working with. This is Peter Hawkes, who is, I guess, on the move from Adelaide in Australia to Nijmegen, because many of us know Marcus Flaum, who is based at Colorado, and Hessel based at Amsterdam, and my colleague at Yan Li Song at my own university, Washington University. So that's the collaborators. Now let me start my talk by, recalling the basics. I hope, So what do I interest here is about SL2R. Okay. So, well, what is SL2R? I guess everybody know it. I do not need to recall it. We are considering, matrices with 2x2 matrices with determinant 1. So here we have real coefficients. And then we look at its maximal complex subgroup. Okay, that's the SO2. Right? Then, well, so associated to the subgroup of SL2R, we can consider the homogeneous space, the quotient. Okay. So here we have the quotient of SL2 mod out by SO2. And we know this manifold is not a compact manifold. This one is non-compact. We can identify them. We can identify the quotient with the natural metric. That's the Poincare disk. Okay. And since it's a Poincare disk, it's a complex, one-dimensional complex manifold. So we have a natural, actually a Kähler structure. We have not just a metric. We have a symplectic form. We have a complex structure. So we'll try to use this in the next slides. So that's the where we start with the simplest possible group, simplest possible geometric space. So now what we are interested in is kind of a very standard operator. So we have complex structure on X, right? Remember just Poincare disk or the upper half plane, we have the complex structure. So we can consider, this Tbar operator, right? So here I just consider the simplest possible differential operator. So then the nice observation, nice property here is because we have SL2R as a group with X on X. So recall that X was SL2 modeled by SO2, right? So it has another SL2 action. So with this action, it's making everything invariant. So the Tbar operator is actually SL2 invariant. So with this invariant property, we know that the kernel of our operator, if we look at holomorphic functions, the kernel of this Tbar here just holomorphic functions on the Poincare disk is actually, as a set, it's SL2 invariant. Right? So since it's SL2 invariant, it has a natural SL2 representation. So this is also true for the co-kernels. So that is corresponding to this H01. Okay? So we have two representations of SL2. So the kind of question we're interested in is we would like to study this kind of the Euler characteristic or the Freight index of our Tbar operator, of this operator Tbar. Right? So here, this one is a representation. This one is also a representation. I'll try to make this part precise because here you can check that for our space X, as is a non-compact manifold, when we consider here, say the kernel of this Tbar operator, the kernel are just holomorphic functions. Actually, this is an infinite dimensional vector space. So to make our study more well defined, we need to introduce more mathematics to make them more precise. Before I do that, I want to generalize this construction a little bit. So here we consider just the Dobu operator, the Tbar. Now we can try to introduce some bundles, some twistings. Okay. So what I will do, people in geometric quantization will do this all the time, right? We try to consider quantization bundles. So here we have, the line bundle. So we consider the one representation, Cn. Well, it's a complex one dimension. I introduced a subindex n because of the weight. Because of, you'll see I have this rotation with weight n here. This corresponded to the SON representation. So this is from the SON representation, we have the rotation Wilding number n times. So from this one-dimensional representation of SO2, we can define a line bundle on this homogeneous space on our Poincare disk in the following way. So SO2 acts on Cn, also acts on SL2 as we had originally. Now this one is a bundle over our X. This is a complex line bundle, actually a holomorphic line bundle. So now what we can do is we can extend the Tbar operator we had now to this kind of forms with coefficients. So that's what I'm going to do. So with the proper choice of a connection, we can define the following kind of operator, extension of Tbar operator. Here I had an index n to refer to this choice of the weight of the SO2 representation. Okay, so now similarly as what we had in the Tbar operator, we can ask the same operator and now the same question, right? We can look at the kernel of this twisted Tbar operator and also the co-kernel of the twisted Tbar operator. We would like to study the Euler characteristic of this operator. Okay, so that's the kind of geometric operators we are interested in on our space, on our geometric homogeneous space. Okay. Now, I would like to make, as I said, for our operator, for our Tbar operator, because our X, this is a Poincare disk, it's not closed. The space is, the infinite dimensional space. So we'll introduce some metric or L2 structure to consider Hilbert space here. So that's what I'm doing in this slides. So we introduce a Hermitian metric on the cotangent bundle, on the tangent bundle, on the line bundle, so that we can talk about L2 space. Okay. So square integrable sections. And now with this L2 structure, this Tbar operator actually naturally extends. This Tbar operator is we have differentiation, so it's not a bounded operator. It's an unbounded operator, but it's a closed operator. So that's the kind of the nice operator we can work with. So actually, it's also elliptic. Okay, so that's this operator we have. Now, with this L2 structure we have on the space of sections, we know that, well, this L2, this Hilbert space structure is preserved by our SL2 action. So this is from my assumption that our metric is chosen to be SL2 invariant. So here we can choose it because our action of SL2 on X is a proper action. So we can make sure that we can choose such a invariant metric and the invariant connection. So with all these invariant assumptions, invariant properties, we now can say that this L2 space is a unitary SL2 representation. So we know SL2 could have non-unitary representations, right? For example, all its non-trivial finite dimensional representations. There are many of them. They are not unitary. But for here, our operator, our representation is unitary. So that's the kind of what we have from geometry, from our study of geometry. Okay. So here, with all those assumptions and with all the requirement of our data, we can now conclude that this kernel of our Tbar operator or the twisted Tbar operator, this is again a Hilbert space with a SL2 representation. Right, so that's what we have here. This is a unitary SL2 representation. Okay. So that's the kind of the representation, where the representation come into the play, and also the type of representations. So they are unitary representations, infinite dimensional unitary representations. Okay. So now we can define our index kind of tentatively as the difference or the element in the representation ring. Right? We can consider, the unitary representations, isomorphism classes of them, and then take the formal difference. So that's the kind of to make our study more precise. But actually, what I will do in the next step is I will introduce some more machinery, more analysis, sister algebras to make this part more concrete. Okay, that's what I plan next. Okay, so before I move on, that's the first part of my talk about SL2, the kind of warm up, the model, the examples. Any questions? Okay, I don't see any questions.
Maybe, yeah, I have one question. So you explained to us that, well, we get some possibly virtual representation of SL2R.
Right.
So what is it? What is this representation?
Oh, I'll come to that in a moment.
Okay. Sure. That's a natural question at this point.
Yeah, thank you. Yeah, Ando, thank you for that question. I will come back to that. Yeah.
And one quick question, I suppose the measure you're using is simply the symplectic measure?
Yeah, here I'm just using the symplectic measure.
Mm-hmm.
Okay, very good. So that's the, SL2. Now, as I promised, I need to introduce a little bit more analysis to make the definition, my study more, precise. So here I want to, first of all, generalize, SL2 to connect the real reductive Lie groups. So what are these groups? Well, you can just think of them as subgroups of matrix group, GL and R, closed under the transpose. Okay. And also we have to require to be connected. Okay. So that's a type of groups we are going to study or focus on in this talk. So these are kind of the natural class of groups we'll consider. And now, well, I need to introduce some analysis. Sorry for that. I need to consider a Hahn measure. So this is an invariant measure on our group. So for this class of groups, actually it's unimodular. So this measure is actually bi-invariant. Okay, then we can consider the L2 space, like what I have already done in the SL2. Okay. So we have a Hilbert space. Now sorry for the. So the next is now I need to introduce some operators, some analysis. So we are considering giving us some complex supported continuous functions on our group. We look at this kind of translation operator. So this is the left regular representation, if some of you are familiar with this terminology. So we have L2G, our group element, so giving us any group element. We can X on a section by doing pullback on the functions. Now, giving us a function here, we can extend this pullback in this form. Okay, that's what we are doing for the, and in this way, we can check that LF, this is a linear operator, which is actually a bounded operator. Okay, this is a bounded linear operator. And using these operators, we can look at a nice, class of operators. That's what we will call as reduced C-star algebra of the group C-star algebra, which is the norm closure of all our operators coming from complex supported functions, complex supported continuous functions. Okay, so this is kind of the continuous functions we'll work with. Actually, there's a nice subset of smooth functions. For us, we're interested in geometry, so we are interested in smooth functions. That's this so-called Haish-Chandra-Schwarz algebra. So this is a class of functions on G that the derivatives have rapid decay. So they actually decay very fast. Okay, so that's the kind of the algebras will be interesting in this development. Okay, so now let me generalize the construction, the operators we had just now for our SL2. So for SL2, we considered SO2, right? That's the compact, maximal compact subgroup of SL2. So now we can just consider the maximal compact and then take the natural quotient. So here is the assumption I'm gonna assume. So these assumptions can be weakened, but for my talk, for the geometric part, I would like to assume this. So basically, I will assume that our X is nice. So like in the SL2R, we had the Poincare disk. It is naturally a Kähler manifold. Now we are assuming that X is a spin manifold. Okay, so it's, and also we'll assume it's even dimensional. If it's not even dimensional, we can also generalize our study, but let's assume it's even dimensional. So with this assumption, we can consider some kind of natural bundles, this so-called spinor bundles associated to our space.
Maybe a naive question. How is it? How often such homogeneous spaces are actually coadjoint orbits, or always, or never, or how is it? Because right before SL2R over SU2, this was there was a family of coadjoint orbits, right?
Yes, you're right. And in general, I do not know, and I do not think they are coadjoint orbits. But for SL2, you are right. It is a coadjoint orbit. But in general, I do not know.
I also have a question. This assumption that it's spin. I suppose that's not a very strong assumption, is it?
So it's not a very strong. Many groups has this property.
Because if you just have a K equivariant spin structure at a point, then you can just extend it.
Right. You're right. Yeah. So now as the kind of next step as a generalization, like what we did in SL2. First of all, here we started with a reducible representation, like the Cn. If you remember, I had the Cn for SO2, the rotations on the lines. Now we are replacing what Cn by this V mu. This mu is the highest weight, right? Like the n. Then we can consider again this line. Now it's not a line bundle, it's a vector bundle. And then we can have also this generalized, operator. That's the kind of, here I use the slash d sub mu to kind of refer it as the Dirac operator associated to the spinors, to the spin. Okay. And then we have, again, now we have the right, language to talk about this index. So I will consider the index, the kernel of this d mu and also co-kernels. They are actually, you can make them precise as the K-theory of the C-star algebra. So what is this element? Let me talk about this quickly in the simple term. So we have this algebra, we have finite generated projective modules. That is, the kind of the object this kernel will define us. Now what we're considering is we're considering the Grothendieck group constructed out of isomorphism classes of finite generated projective modules of this C-star algebra. Okay. So you can see that, well, we are considering representations actually of this reduced group C-star algebra. Okay. So that's this index element. Now, what we are heading toward is to introduce this tempered dual. Okay.
Comment?
So, yeah, please.
Yeah, so you basically described assembly map, right?
So, Richard, yes?
So you described assembly map, right?
I have
But until now it was
term.
assembly map, right?
Thank you for bringing that up, Richard. Yeah.
So it's you get the answer to Anton's question. You get those co-integrable representations.
Right. Well, you are right. The right terminology or the term in non-competitive geometries. This is the, as Richard pointed out, this is the assembly map. Yes.
Yep.
For the Kahn-Kasparov isomorphism. Okay. So Thank you.
But we don't need to understand those
Yeah,
words.
you don't need to worry about it. So that's why I did not
Right.
mention.
No,
Yeah.
so
I already forgotten, right? All this.
so Anton,
Yes.
the one thing you do understand. So there's a construction of discrete series due to Atiyah-Schmidt. That's what it is.
Right. So yeah. So all you need is just to take what I told you about geometry. So this.
Oh, in particular, you promised to tell us about representations. So this is discrete series, right?
Right. Well, not all of them are discrete series, but most of them are.
Okay.
Yeah. Okay. So now let me get to this definition of temporal dual. So using this cyst algebra, the definition is very simple. It's basically the space of isomorphism classes of reducible unitary representations of this cyst algebra. But, if I want to formulate it using the G representations, it takes more efforts. You have to look at the matrix coefficient and talking about how much the growth, and also you have to look at the Chandra, the Planck measure, the support. But for us, if we work with this terminology, it's just the representation of this reduced cyst algebra. All you can see that this is all from our study of L2, the left regular representations. That's kind of this part of representations we can see. Those do not show up in L2 of G. We will not see them. Okay, and on this set, there's a natural topology. So that's the Fell topology. And if you are familiar with algebra, that's the Hall kernel topology. Basically, you look at the representation and ideals, and then that define as some closed set, and use that to define the topology. So that's the space, the set we are working with. So now let me give you some examples. Let's start from a simple example.
Excuse me, Xiang, can you say where the term tempered comes from? Is this the dual of some rapidly decreasing function somewhere?
Well, so this tempered is kind of from requiring if you look at the matrix coefficient, they are growing relatively nice.
Okay, thanks.
Yeah, so what I mean is if I choose two vectors, X and Y in the representation, then we can consider G act on X and Y. We can ask about this growth of G as a function. This will define a function on G. So we can ask about how fast does this function grow. The tempered kind of saying that this function are growing relatively nice. Okay, so that's this. Now, well, for the simplest possible group, in the case of G is R or Rn, or the connected abelian group, we know the representations. Well, actually, lambda does not really matter. It's just the dual, and here just well, just be careful when I write this one. This is the space. When I had G here, this is the group. So luckily or kind of accidentally here, the space and the group are same, having the same symbol. So now we had here, this is the group algebra. Here is actually just the multiplication of functions. It's pointwise multiplication. And then we can see that's how it's, what is the space we're looking at. So that's for the abelian groups. Now the next piece is the compact group. In the case of compact groups, this is down to so-called Peter-Walsh theorem. Okay. So it tells us for compact group, we have only finite dimensional representations. Actually, they are all unitary. So we can decompose this algebra into just this kind of direct sum, infinite sum of matrices. So it's an infinite sum, but every component is just a matrix, finite dimensional matrix, matrices. Then we can have this description of G lambda mu. Here, it's a discrete set. It's a discrete set of all this kind of kind of the dominant weights up to isomorphisms, up to some equivalence. Okay, so that's the kind of the tempered dual or dual. So here again, there's no distinction between this tempered or just general representations. Okay, so that's this. Compact group. Now let me get to this SL2R, our example. So for SL2R, it's getting more interesting. So it's not just discrete, it's not just connected, like the two examples we saw just now. So actually there are three parts. So what are the three parts? So there is a part actually is discrete. So that's this part, the part with long zero integers. So remember in my examples, we had the construction from Cn. Okay? So we have all these line bundles like the geometric quantization. Then we had all this kernel or co-kernel. And here for n not equal to 0, all these representations, actually only one of them contribute. Not all, they cannot be non-zero simultaneously. Either this one or this one, depending on n is positive or negative. And each of them actually is a discrete series representations. So if you are not familiar with this term, just forget about it. What I mean here is discrete really just refer to here in this tempered dual, this topological space I just described you, these points are discrete. They are isolated points. Okay, so we have a bunch of points indexed by n. They are like the holomorphic functions, holomorphic forms, and then weighted holomorphic functions. If you are, so that's the kind of this objects. Okay. So that's the discrete part. And then there is a part looks like this. So why is like this? I'll explain to you in a moment. So in representation theory, people usually draw this like, we have, so when we have a Z2 acting on R by reflection, basically we think here we have the positive line, but now at 0, we have actually kind of 2 points. Okay. So that's the 0 component. So this actually corresponded to n equal to 0. So this is not the discrete series. That's called limit of discrete series representations. And then for the SL2R, there's another piece. The another piece is this, another connected piece. So this is actually R mod Z2. So why do I call this? I'll explain to you in a moment. But in representation theory, if you draw the tempered dual, that's like this. So this is just a semi-line from 0 to infinity. So, okay. So the difference between 2 and 3 is if you look at this, Planck measure, for this third one, Planck measure actually vanish. For this second one, Planck measure does not vanish. Okay. But now that's the kind of the picture. Let me explain to you why do we distinguish 2 and 3, because for us, for geometric spaces, well, this seems like almost the same. The reason is for this algebra, if we look at this algebra, you can study its structure. Then by study the structure carefully, by here, this means Morita equivalence. So up to Morita equivalent, if we are only caring about representation category, then it's like the following. So for the discrete part, it's every component is basically just one copy of C, or you can say one copy of compact operators on some separable Hilbert space. For this part, we have this cross product algebra. So it's a semi-direct product. This is a non-commutative algebra. And then for this part, it's like this algebra. So this is a continuous functions on this quotient. That's why we had this 3 and 2, they are different. Although for action, it seems they are the same.
Can you relate these classes to the coadjoint orbits of SL2R? I think the first one are the certain ones of the hyperboloids with two sheets.
Yes.
And maybe is 2 or 3 the principal series, which would correspond to the hyperboloids of one sheet.
3 is the principal series. I mean, both are principal, but so one is spherical, the other is non-spherical. So this one is not, I mean, non-spherical principal series.
Yeah, but that's the cone, right?
Right.
The singular cone.
Yeah.
But there's only one. There's
Yeah,
only one cone, rather than a family of them. Yeah.
But for coadjoint orbit, that's
So the point is that there's not a unique representation associated to that coadjoint.
But you're saying that 2 anyway.
Here, what I'm saying is this is a family. So what I'm saying is for this one, for each of this, each point on this, I mean, each point here has a representation. They are not isomorphic.
Mm-hmm.
So it's
But they correspond to Plancherel, vanishing Plancherel measure. Is it right? 2.
No, so all these have long vanishing Plancherel measure.
Okay.
So 3 has vanishing. 3 is vanishing. 2 is not.
The 3 has vanishing Plancherel measure at the origin.
Oh, okay.
Yeah. So the distinction between 3 and 2 is for 2, the Plancherel measure does not vanish. It's the code. If you kind of, it's not a coach, but then for this one, it's actually vanishing.
Okay.
So that's a distinction between 2 and 3. Okay, so that's about this SL2. Okay, so now let me just get to the kind of principle I would hope to explain to you. So the principle is we would like to view the cyst algebra as the continuous functions on the dual, and the Schwarz algebras, the kind of the fast, rapid decay smooth functions. These are viewed as the smooth functions on the dual, and then the K-theory of our algebra. Actually, for these 2 algebras we have, the K-theory, there's no distinction, just like what we have for manifold. Smooth K-theory or topological K-theory, there's no difference. We view them as K-theory on the tempered dual. Okay, so that's the principle we would like to use to study our our algebra and the dual. So now this is a kind of the structure I would like to explain to you in general. So in general, if we have this connected real reductive Lie group, what do we know is, Westermann studied in the 80s, and then more recently by Clare, Crisp, and Hickson. What we know is in this generality of connected real reductive Lie group, we can have a similar decomposition. Okay, so the P and the sigma does have some meanings, but for our understanding of the talk, just think about our algebra is decomposed into pieces. Okay, so the meaning of this P and the sigma is not really necessary to understand my talk. I included them just for experts here. For some, we have some experts in the audience. Let me continue. And then for each piece, actually the behavior, the algebra looks very similar like what we had. So we can have a abelian group. So this would be like an R we have, okay? And inside associated to this abelian group, we have some finite group. That's the Z2 we had for SL2. Okay? And this finite group looks like the following. It's a semi-direct product of some 2 groups. So this one corresponds to the 3, it's going to give us the quotient. This one corresponds to the cross part, to the second case, Z2 action. So that's the kind of picture I would like you to keep in mind. So that's so for each piece, this is the geometric kind of algebra, geometric space we're gonna kind of look at. So for this part, do not worry. And the P for experts, that's the cuspidal parabolic subgroups, and with some equivalence class here to be put. Let me. Okay, so that's the structure on the sister algebra, on our algebra. Now, this is the study from K-theory, like what Richard mentioned, from the study of group sister algebras and also this Kasparov conjecture or isomorphism. So it turns out in this description of the the direct sum, this whole decomposition, we have the temporal dual into different components, right? Only kind of two parts contribute. That's the kind of a very interesting or remarkable kind of a simplification. There are many, many components, but for K-theory, only two components contribute. Not two components, two parts, I should say, two types of components. So what are the two types of components? These are called the essential components, okay? So these are the components. One is the case such that, the group is trivial. So there's no, so the W sigma group, the group is trivial. Then we just have, this kind of simplest possible space in our temporal dual. It's just kind of a vector space. Another component, that's the kind of interesting component I want to bring your attention. So another component is this case, that's kind of the number 2 case in the SL2. So that's the case, sigma, W sigma is just R sigma. It's just like the copies of Z2. And they have the same rank, same number of Z2s as the rank of our AP. In this way, we have this algebra, right? So this is, so this part is just functions on some vector space with dimension, say this one, and R sigma X on this space by hyperplane reflections. Exactly the same kind of dimension number of reflections. So that's the nice component we'll work with. So the result proved in sister algebra is this part and this part, they have non-trivial component of K-theory. And actually, a lot of people contributed to the study of this K-theory and the so-called Kasparov conjecture. So, the people now know actually Richard in our audience contribute very, fundamentally to this study. What Richard showed is, together with his collaborators, for actually connected, almost connected. So groups with finite number of components. The map I described with a correct generalization would be an isomorphism for the K-theory. So it's a very general result. So what I'm kind of studying here is I try to single out the nice pieces, the nice groups, and try to see some more geometry. Okay. So that's what we are looking at. Okay. So now let me get focused on these two components, right? So just now we had one component, that's this simple part, the simplest possible space we have in. So we know it's geometry. Now I want to look at these two parts, right? So that's what I have here for these slides: multi-vector fields, Poisson structures, and the formality and the deformations, right? So for this essential components, for the simple part, it's easy. It's just here, this one is just the vector space. And we know it's Poisson structures. We know formality. We know how to deform the Poisson structures. We know a lot of things about this. Right? So now that's for the kind of the remark for the first part. The part for the second part. So second part, we have a non-trivial hyperplane reflections. But now, interestingly, this hyperplane reflections has the same number of the dimension of the space we have. So to understand the deformations or the Poisson geometry or non-competitive Poisson geometry of this component, we need to look at Hochschild cohomology of this cross product algebra. And then, you know, maybe the whole Hochschild complex, not just this H2, but maybe higher. But now with these special properties, in general, if we have a finite group acting on a vector space, looking at this type of algebra, the whole Poisson geometry or its deformation theory is still under development. It's not fully understood yet for formality. However,
sorry, what's the Poisson structure on that component, AP hat?
Oh, so here there's no Poisson structure. Yeah, we can introduce any, then deform it.
Oh, but is there any natural one? What would be?
So here I do not know a natural one.
Okay.
Yeah, so here I do not know a natural one. But, you know, in principle, you can just even consider constant ones and deform it.
Okay, thank you.
Thank you. And now what I want to say is, you know, for this second part, for this cross product part, it's very kind of nice here because of the structure of the groups. What do we know is, if we look at Hochschild complex, Hochschild cohomology, the cohomology, is just invariant vector fields. So in general, the phenomena is, you know, for such a cross product algebra, when we consider Hochschild cohomology, it's like orbifold. We will have, you know, all this fixed point data contributing to this computation. But because of this hyperbolic reflections, the number of them exactly coincide with the dimension. There are no fixed point contribution. It's just like this. Just the invariant vector fields on this space. And now for this type of vector fields, for this type of Poisson structures, we can have, you know, this formality theory developed by Dolgushev and then more recently by many experts here. So here I would like to bring your attention to some nice Poisson structures. So for example, we can conceive our AP has two dimensions. Now we can just consider x dx, y dy. Right? This would be the natural invariant because my Z2 will map x to minus x, the other Z2 map y to minus y. And this one, each of them is invariant. This is the natural invariant biovector, and this is actually kind of the log symplectic or the natural invariant Poisson structures. And for this one, we know how to deform this algebra. Also for, you know, the ones here, right? For this part, we know how to deform this algebra. We have all the theory there. So we know how to deform the category of representations. But the question I hope to understand in the future is, what is the corresponding deformation of this cyst algebra, or maybe at the level of Lie theory, like the universal enveloping algebra? What's the kind of, once we deform our space along all these directions, these are nice directions. We know there's no obstruction in deformation theory. What's the corresponding deformation? Yeah.
A very naive question.
Yes,
is there anything corresponding to quantum groups in this deformation theory, or is it a wrong intuition?
I like your question. Actually, I think there's something in that direction, but I do not know the answer. I hope, you know, our experts here would tell me, yes, that's the quantum group, or some quantum groups correspond to this. That's why I wanted to talk this here.
Okay, thank you.
Thank you, Andrew. Yeah. So here we have all these natural deformations of the temporal dual of the group, kind of the algebra and the representation category would be the natural examples, or it must be something like a quantum group, something there, but yeah. Okay, so that's about this slides about the deformations and relation to the geometry. So now, so that's the second part of my talk about the geometry of the temporal dual. And in the last about 9 to 10 minutes, I will discuss the kind of applications in the index theory. So any questions?
Can I ask a question first?
Yeah, please.
Hi, I'm just wondering for such cross-product algebras, when you want to compute the Hochschild cohomology or Hochschild homology, what is the method that you're using? What's the method that you would recommend?
So maybe that's a talk discussion we can do afterwards, but the idea here is you have to do some resolution. Maybe that's the vague answer I gave you as a kind of during the talk. How about that, Marco?
That's okay.
Some resolution, and then you can compute.
Maybe just one comment. When you write H star, you do think about cohomology in some category of topological algebra. So your tensor products are not algebraic tensor products, right?
All right. Yes. Thank you, Richard. I have hidden them under my rack. I did not mention that. So here, this needs to be a kind of topological or bological algebra, and here this needs to be kind of the put into the right category of modules, right category of cochains. Okay. Yeah, thank you. Okay, so let's move to the next part. So remember, we are interested in this index element as the motivation of our study today. So, so now to study this K-theory element on this topological space, well, we know we can use chain character to map into, this cohomologies, right? So you can have the chain characters to map into the cohomologies of the space. The space is, kind of not a very kind of smooth manifold, but still you can think about, intuitively we can use chain character to map into the cohomologies. Then if we are interested in defining some characteristic numbers, then we need to consider differential currents or homologies to pair with these cohomologies, right? So that's the natural kind of a question we would like to study. And then to make this study of homologies and cohomologies, more kind of rigorous, actually, I mentioned here, this is the second homology of this Schwarz algebra. Here we have to use the Schwarz algebra, not the sister algebra. That's where we need the smoothness. Okay, and also we have to consider some kind of bounded or kind of right framework of homology, not just purely algebraic. Okay, so now for this case, for the Rn case, for the R case, what do we know is, well, as I already mentioned, the Schwarz functions is identified as Schwarz functions. Well, here just a rapid decay nice functions on our vector space Rn. Then the nice currents, nice homology currents, we can write down, well, you can compute this one. If we consider complex supported homology, then it's basically like this. We have only one dimension contribution. And then you can write down a nice currents. That's just, the standard currents. We do integration. We have F0 to Fn. We consider the simplest combination of our functions, put them together. And with the rapid decay assumption, we know the integral is well defined. It's continuous. It's a nice continuous function. Okay. So that's this kind of example in the case of Rn. Now, this is on the dual. We can try to write it on the group case, on the group. So when we write this on the group, well, this is just by doing Fourier transform. So no magic here. It's very straightforward. You just do Fourier transform, then you'll realize the nice determinant function showing up. So before we had this df0, df1, df2. Now we have to use this determinant function, which is written in the following form. We have the determinant function and then some kind of, the convolution of our f's. So here, when we talk about phi, these are convolution algebra as convolutions on our group Rn. Before it was just pointwise multiplication. Okay, so now I'm short of time. Let me just be quick here. So in these slides, what I wanted to tell you is, so let me just be short. You can generalize this construction to our general group, okay, by playing with this kind of Iwasawa decompositions, by single out the right component of our abelian part. Okay, so that's the kind of the punchline here for my slides. I have to apologize for my quick movement for this part. Then you can.
But maybe it's just a short question. This C, which replaces the determinant, what is it now?
This one is defined using the map. Defined using a map. Right? So here, so C just now was a map from H, from the function that we called H, from Rn to Rn, the identity map. Now, for this case, what we can do is we can generalize this to have a function G from G to A.
Okay.
Okay, and then again, you can have the H like the coordinates, H1, H2. You can see here, that's the rank, the dimension of the A group, M components. Then you use determinant to make it into the, and well, here you have to be careful because of the K. The K is there, so it's not totally commutative. So we have to involve some conjugation of K to make this definition of C. But that's the rough idea. Okay, so that's about this generalization. Now, what do we know is we can prove that with, Yan Li Song, Yan Li. So what do we know is this phi is actually satisfied, is the right, co-cycle we want. It is a cyclic, it's a Hochschild co-cycle, and actually it is a cyclic. Okay, so it's a nice right object in the, so as if you're familiar with the cyclic cohomology, this one corresponds to closed differential currents. So that's what we would like to have. Now, to end my talk, let me tell you quickly what we can do with this cocycle. So now H is the Cartan subgroup of G. Now we take the kind of the compact part, that's the T part. And then we work with some assumption about, so here I assume, so in general, this intersection may not be the maximal, compact subgroup, may not be the maximal torus of M group, but here we assume that this intersection is the maximal torus. Now with that assumption, what we can prove is, so we had this Tbar operator, and then we can compute the pairing. So now this is the cocycle I wrote down using the integrals, using the determinant. This one is the K-theory element from the geometry, from the polymorphic vector bundles, and then the Dirac operator. Now what we can identify is we can see that this index pairing is really giving us some nice information of the representation. So here is the character formula for the representation associated to V mu. This is the Y denominator, as I mentioned here, so which is the sum of the roots and then taking the exponentials. Okay. So this tells us using this co-cycle using the differential currents, we can cover some nice representation information of the V mu. Okay. So another part is how about the topological formula like the Tbar? So that's the next slide. So actually you can use some geometry and then use the fixed point of X to write down some Tbar type of localization and index formula. Okay. So that's this result about the topological formula. So that I think my time is up. Let me stop with this. Thank you.
Oh, thanks a lot. Do we have any questions?
I have a naive question about the last slide.
Yeah.
So this was a localization on which space, right? You say the right-hand side is a kind of localization formula, but I mean, from which space to which space you localize?
Thank you. So to ask that question, this gives me more time to explain the formula. I was quick with the short of time. So in principle, this integral, this pairing is on, remember, it's on the X, right? The G mod K.
G mod K, yeah. M
So our operators is on G mod K, the bundle is on G mod K. The cocycle what define is kind of, you can make it on as a group, as a cocycle on G. So this is an integral on X, some formula on X. Now, what we are localizing, we had this X, we are localizing the whole formula into the X fixed point on the homogeneous space respect to M. So M was in the Iwasawa decomposition of, so our G looks like K, M, A, N. So it's kind of the localization to this, this Y part, fixed point of X on Y. So in the good cases, when X is the, a regular element, then this YX would be just a few points. So the integral will become just counting numbers with the right weights, and then it's the sum.
Okay, thank you. And is the formula above a particular instance of the formula below? The formula with this sum, with this alternated sum over the wide group of K?
Thank you. So that's a very good remark and suggestion. Actually, we can derive this formula from this. Okay. So we can derive using the local geometry and then like an Tbar.
Okay.
We can derive the character formula using their localization, the fixed point theorem. So there's a way to derive this character formula, but yeah.
Okay, thank you.
Yeah. So another remark, Andrew, so here we are focusing on X equal to G mod K, but this theorem actually is proved in a more general setting. You can consider any manifold with the proper G action such that the quotient is compact. And then with a G invariant elliptic differential operator, then the similar localization formula could also be obtained.
I think I have a question myself. So this formula for this cyclic cocycle was first flying by very fast. So you have this very explicit formula, right?
Yes.
It was vaguely reminiscent of my own talk with Van Est. So basically two questions: is there a connection with Van Est, and secondly, is there some conceptual explanation where the formula comes from?
Very good question. So here we have so for this one, it's so I started with the motivating example of Rn. So this one, This one is actually from Van Ness.
Mhm.
So it's from, here the Lie algebra, the group, they are, the exponential map is just identity. So this one is from Van Ness map. So in the cocycle we wrote down for general G is not, I do not know an easy way to construct it from Van Ness map.
Mhm.
On the other side, what I can report to you is we do have this work a few years ago with, Marcus and Hessel. We can have the following map from the relative Lie algebra cohomology to the cohomology of G. This is a Van Ness map. And then we can use this ones to define some cyclic cocycles. This can also be mapped to cyclic cocycles on the algebra. But these ones are not same as this, which one? Are not the same as the cocycle we constructed here for this Poisson, not as this one in general. So even in SL2, we have actually two constructions, two cocycles. They are not, identical in the cyclic cohomology.
So if I understand correctly, in principle, you just came up with a formula. There's no.
Well, so it's not
for the cocycle.
Well, it's not coming up with a formula. The formula is from, remember, we have the geometry of the tempered dual. So we have Rn. Even in the general case, we still have the geometry of the tempered dual. We have those components. Mm-hmm. So there we just use, we know it's homology. We know it's cyclic homology. We know it's the currents. What should it be like? So things there exist. It's already there. So in some sense, we need to do a Fourier transform, but using Planck formula, some generalized Fourier transform. So in some sense, the formula we wrote down here in these slides, in this formula, this is the Fourier transform of the integral on the tempered dual. That's what we would like to view it.
Mm-hmm. So I see Jacobus also has a question.
Yep. Hi, Ken. I'd like to go back to Richard's observations about the assembly map.
Oh, you do the assembly map. Okay, so that's okay.
Yeah, well, you don't have to go back, but I would like to go back. It reminds me.
Yeah.
There is a paper by Nigel Hickson and Jonathan Bloch, I think, where they recover the Weil character formula from the Baum-Cohn, from the assembly map.
Yes, you are right.
I was wondering if your formula, of course, it takes into account the components of the tempered dual. So if there is a flavor in terms of Baum-Cohn in your formula as well, if it is related to this philosophy of Nigel and Jonathan.
Well, how to put? I have avoided all that discussion. You can see I'm not trying to attract our audience to the Baum-Cohn or the Kasparov. So here, you are right. There's suddenly, you can see from as I mentioned, which kind of got us to study all this essential component is from the study of Baum-Cohn or Kasparov. Then actually using the cocycles here, using the understanding here, one can do is one can try to give a proof of the Kasparov isomorphism using using the cyclic cocycles, using the understanding of the essential K theory.
Right.
So that's a joint work with Nigel Hickson, Pierre Claire, and then Yan Li Song. So yeah, so that's what we are working on.
Okay, do we have any other questions? No, I'm looking raised hands or something. But it does not seem to be the case. So yeah, let's thank the speaker again, I would say.
Thank you.
So what's our speaker for next speaker? I forget. Somebody know?
Me.
Ah, Misha, right. Next week it's going to be cluster algebras, I suppose. Yeah, looking forward.
Yeah, Michael. Yeah, yes, yeah.
Okay, well, thanks everybody for coming. I think I have to leave and get myself some lunch. So, bye-bye.
All right. Thanks, everyone. Thank you for the talk. Bye-bye.
Bye-bye.
Thank you.
Bye, Xiang.
Bye.
Oh.